Good afternoon, everyone. So for today, I'm going to discuss forcing functions and their responses as applied to first order systems only. So what would be the corresponding responses of the commonly encountered forcing functions if applied to first order systems? Now, when we speak of the dynamic behavior of our systems, process dynamic and control systems, that is, it is very important that we know how our process variables will respond to specific changes in the input, which are actually outside of the control of the computer or even of the human intervention. So a number of standard types of input changes are widely used for two reasons. So we are only discussing here the commonly used representations of this particular input changes. They are used because they are already representative of the type of changes that occur in plants, and they are easy to analyze mathematically. With one of these five forcing functions already used to simplify its real counterpart. Now, the easiest, if I may say, of the real actual representation of a disturbance in which a particular process may be subjected to is the step input. So the step input, if applied to a real process, could be viewed as a sudden change in a process variable, which can be approximated by a step change of magnitude anything. It could be letter A, it could be letter B, or any letter that you would like to represent the magnitude of. So from our textbook by Kohanor, so we mathematically represent a step function of magnitude A in terms of capital X of t being equal to A u of t. Now, this is already capital class. I'm referring to the x of t because this is already the deviation of the input variable from its steady state condition. So, if you recall, this is already x minus x sub s, where x is its current condition and x sub s is its steady state condition. So, this one now is already representing how much has the current condition of the input variable x has changed based on the steady state condition or from the steady state condition. So u of t, as encountered in advanced engineering mathematics and in chapter 2 of our book on review of a plus transform, is just a representation of the unit step function. So in here, our magnitude for the step function is a. On the left, you get to see the graphical representation of a step input of magnitude A. So the reason you are seeing this vertical line projected here to the right is for you to be able to see how high is this vertical line from the horizontal axis T. So actually, it's right on the origin, but it was shifted to the right just for you to see what is really happening in terms of magnitude of change to x. So you get to see that this x is equal to 0 for t less than 0, that is for time which is negative, and the value of x will be a, this is the magnitude for t equal or greater than 0. So for all our disturbances here in process control, we always start counting at time equal to 0, or we start measuring its effect at time equal to 0. The time when such a disturbance happened. So for this particular unit step function u of t of magnitude a, the Laplace transform of which was also discussed in our previous discussion is a over s. So the transform of this function a x of s is equal to a over s. A step function can be approximated very closely in practice. So another example cited here is a step change in the flow rate, which can be obtained by suddenly opening a valve. Or if you suddenly close a valve, there's also a sudden and sustained change in the particular variable. So take note of the term, it's a sudden but sustained change. So meaning, for t equal to 0 onwards, the same change in the input of magnitude A is observed in your input variable. So the step change occurs at an arbitrary time denoted as t equal to 0. And this is true not only for step input but for all types of inputs. Now, since we know already that a sudden sustained change in a particular variable is a step input, then we should know what is its response. So the response to a step input of magnitude A would be this equation that you are seeing here. So there's no need for you to go to derivation because we have discussed already the derivation of this. Just take note that for a particular forcing function, you know the corresponding response to such forcing function. And there's no need for you to go back to derivation. So this one, for any time elapsed starting from time equal to 0, this equation will help you determine the deviation of the output y from its steady state value when a step change of magnitude A in the input was observed. So notice that this formula is only applicable for time equal to 0 and onwards. So it does not have any essence at time less than 0. You get to see an equivalent graph of this particular response of a step input in our textbook by Kauhanor. I chose this one because you get to see how much of the ultimate input after a certain time was already achieved by your system or was already reached by your system. So after time tau, this is t, which is tau, your system already reached 63.2% of its ultimate value, which is 1. So we expect that the value of this particular equation ultimately will be A because we have this magnitude A here. The graph that you are seeing here has an ultimate value of 1 because this one is for a unit step response. Well, this equation is more general because this one is for a step response of magnitude A. So after time t, which is equal to tau, we go back, the response of your forcing function reached 63.2%. After 2 tau, it reached 86.5%. After 3 tau, it reached 95%. After 4 tau, it reached 98.2%. 5 tau, it reached 99.3%. As we increase the time, we will ultimately reach the ultimate value of the response, which is 1. So if the magnitude of your step input is not 1, all you have to do is multiply the percentage here by that magnitude of the input. That is already the magnitude of the change of your output based on the change in the given input. And that is when we speak of the step response. So again, for a step forcing function, this is our forcing function equation. This is our Laplace transform. The response is this. Okay, so it's a generic representation of the response in the same way that this is also a generic representation of the forcing function. So that's when we speak of the step input. Now we go to the ramp input. Where do we use the ramp input equation in real physical systems or real industrial processes? So examples cited here are ramp input could be seen in industrial processes which experience drifting disturbances. What are these drifting disturbances? These are disturbances that shows relatively slow changes, either increasing or decreasing for some period of time. But that particular increase or decrease has to be noted to be a constant. Why am I saying it's a constant? It's stated here. It's because the change is that similar to an equation of a line if you're going to represent the particular equation. So you could see here that this line has a constant slope of b. So the slope of this line is constant b. So meaning the increase of this particular variable f of t is b, constant at b. So that is in the case of the ramp input. It could be a steady increase or a steady decrease as long as the term steady says, it is constant. The rate in which the change is to be observed is a constant. Now, graphically, this is how we represent a ramp function. So, if you're going to write its equivalent in an equation, this is our function of t. It's a function whose value is equal to b times the t, as t is equal or greater than 0. Otherwise, at time which is negative, it does not hold any value. So if you already have in mind the step forcing function equation, its Laplace and its graphical representation, add to that the equation for the ramp and its graphical representation. Now what you have here is a straight line of slope b. In our case, it's b. The slope is b. This slope b is called the amplitude or the magnitude of the ramp function. So I will have this edited slide later, the one that I have uploaded. This should be a b because I changed the magnitude here to b. So nonetheless, whatever is your slope here, that should be the slope of your line. This should be b, and this should also be b. Now we move on. This is the response of the ramp forcing function, wherein the magnitude was changed to b. I really intended to use b because our textbook, our general reference book, used a magnitude also of b. So to eliminate some confusion, although it could be really any letter for that matter. So we have bt minus b tau times the quantity 1 minus e raised to negative t over tau. Or if we will simplify, since both terms has the b, we could write this as big B or small b, doesn't matter. We multiply to t minus tau plus b tau e raised to negative t over tau. So you have the equation of the forcing function, and you have the response of that particular forcing function we call the ramp forcing function. In terms of its response, if it is curved or graphed, this would be the representation of the response. This is our response curve. If you plot this line, that line would be this, and this is our original ramp input. So after an initial transient period, the response is parallel with the input. So that transient period you could see is probably with until here, 4. And after this 4, more or less, we see that the response curve or line is already parallel to the input representation, which is that of a line for the ramp input. So they are already parallel. Whereas in this part, initially, they're not. But as we proceed, or after long exposure to that steady increase in the input of magnitude b, now the response is behaving more or less similar to the input. And they are now lines which are said to be parallel. So what is the steady state difference between the input and the output? When we speak of steady state difference, you're going to base it on the part wherein the two curves are already parallel. And that steady state difference between the input and the output, this is your input and this is your output, is this particular value. The steady state difference between the input and the output. So the difference of this from this at the same time reference is the difference that is being mentioned here. And that is equal to the magnitude of the ramp times the time constant tau. As to how long will the input be ahead of the output, or shall I say, as to how long will the output always lag behind the input, that should be in terms of the tau. So in this case, for ramp forcing function, the output will always be lagging behind the input by a time value equal to the time constant. Whereas as to the difference between the input and the output, it should be the product of the b and the tau. But it would be it could be noted also, class, that after a very long time wherein we have already observed a parallel representation for the input and the output, this b tau will just be simply equal to tau. So after a very long time, your input will be bigger or will have a difference from your output by a value equal to tau. In that case, in here, the difference of this from this would also be tau. Anywhere here, that's b tau. That's for the ramp input. Now, for the rectangular pulse, you encountered this first when we discussed properties of Laplace, and we added this under the properties because this one is not discussed in advanced math. So, if the step input is for a sudden sustained change, the rectangular pulse is a brief sudden change, meaning the change is not sustained. It was not sustained, so it's sudden, but it's just a brief change. In this case, the representation is something like this, if you recall. So you have the magnitude of the pulse to be 1 over h, and the duration is h. The pulse does not hold any value at time less than 0. It does not hold any value at time greater than h. Its value is on the time interval 0 to h, that particular brief time in which that particular disturbance occurred. Now, as to its Laplace, so we have its representation here. As to the Laplace, this would be the representation of the Laplace transform of a pulse function. The magnitude multiplied by 1 minus e raised to negative hs, where h is the duration of the pulse. And then we divide it by s. Now, this particular changes or representation for changes in actual processes could be representing reactor feed shut off for 1 hour. So meaning the feed to a particular reactor or to a particular physical system was just shut off for an hour. It's not something sustained. So this 1 hour is the duration h here. And as to how much has been the change from the value of the feed of the reactor from the time that it was closed, then that would be simply the value of the previous reactor feed, whether it's be volumetric flow rate or mass flow rate. Okay? And then another example cited here is the fuel gas supply to a furnace which is briefly interrupted. So if there's an interruption in the fuel gas supply to anything for that matter, that particular change or interruption is something that is not forever. So it's only good for a certain time interval. So we say that the input change is just that of a pulse. And this is the representation, and this is the Laplace forcing function. Now, the fourth type of forcing function is the sinusoidal input. Now, these particular representations are for those changes that seem to recur over a period of time. So for processes that are also subjected to periodic or cyclic disturbances, recurring disturbances over similar period of time. So we represent them by a sinusoidal forcing function. The equation for a sinusoidal forcing function is this. X is equal to a sine omega t. Omega is the radian frequency. Again, this x is 0 for t less than 0, and it has a value only at time equal to 0 and greater than 0. If it's plotted, class, again, this was just projected to the right, so you will get to see the actual curve. So this is at time 0, and the disturbance happened at time 0, and it's something periodic. So if you notice that this part here is already, that this part here until here is already a repetition of this one. It's just like you copy this part of your curve and paste it here. It's a cyclic disturbance, so it is to be represented by a sinusoidal input. Now we refer to the A as the amplitude of the change and omega as the angular frequency in radian per unit time. Now, if we represented the forcing function, the sinusoidal forcing function, as a sine omega t, its Laplace transform is this: a omega over s squared plus omega squared. If this is the Laplace transform of this forcing function, now let's look at its response. So the response of a sinusoidal forcing function of magnitude A is this particular equation. The first term is the non-periodic term, and the second is the periodic term because of the sine function in here. The phi here is defined as the phase log. It's a phase log because its value is always at all times negative when computed. But it is worth noting that this phase lag is always less than 90 degrees. I have written here that for sinusoidal forcing functions, the amplitude ratio, the ratio that is of the amplitude of the output to the input, it's always less than 1. Why? Because our output, this is our output, the red one, and this is our input, in terms of magnitude, is always less than the magnitude of the input. So amplitude ratio of the output to the input would be this. Without the A, you take out the A, the amplitude ratio is 1 over square root of tau omega quantity squared plus 1. If you will compute for this, be sure that your value will not exceed the value of 1. If it does, there's something wrong with probably the formula or the values that you are using. So take note that the period of our function here was measured from time 0 up to some time wherein the curve again tends to repeat itself. So this is one period. After this one period, you get to see the same curve repeating itself over and over again. The same is true for the output. If this is the one period of your output, then another period is this, then another period is this. So the output will tend to also be cyclic in nature, meaning it's going to recur over time, repeat itself. You see this delta t? This delta t here is the lag time. How much did the output lag behind the input? That's the delta t. Now, in our reference book by Kauhanor, the period was measured from one peak to another peak. That is okay. That is also the period. Or it could be also measured from the alternate crossing of the curve. So I have one crossing here. Then the next crossing that I will account for is this, alternate crossing. So this is also one period. Okay? So that's how we account for the period and the lag time. Now, there are conclusions or generalizations that could be derived out of this superposition of the two graphs of the sinusoidal input and the sinusoidal output. Now, the output is, if you could see, is still a sine wave with a frequency omega equal to that of the input signal. So, meaning the frequency of the output and the input are just the same. This one I've mentioned already. The ratio of the output amplitude to input amplitude would be this, and this is always smaller than 1. And this is giving us a new term, which is the attenuated term. So meaning the signal or the amplitude of the signal was decreased. Attenuation is another term used in controls for a decrease in value. So the signal decreased in value, and it is expected really to decrease. Now, the output will always lag behind the input by a value of the angle phi, and lag always occur because the sign is always negative as stated. Now, if you notice in this particular output plotting of the sinusoidal forcing function, it's already periodic in nature, because in controls we are after actually with the ultimate periodic response or the frequency response. And if we want the ultimate periodic response, we don't anymore consider the non-periodic term here. Although this is the actual response equation, but we only look into the periodic term. We take this out of the picture. So that's it. So this is the ultimate periodic response, or the steady state response, as you could see here in the subscript S, for a sinusoidal forcing function. Now, for the impulse, if you remember what I mentioned, that one of the representation of the forcing function is just a mathematical approximation when we were discussing Laplace transform, this particular representation is the impulse representation. If the pulse happened for a very, very brief amount of time, or the disturbance happened for just a fraction of a second, that could be approximated to an impulse input, because the output that you will be getting, if you approximate it to an impulse input, is more or less the same as that when you represent it by an actual pulse. Because in actual, it should be represented by a pulse, but since it only happened for a fraction of a second, then we have the option to use the mathematical approximation, which is the impulse input. So when does this happen? So in electrical noise spike in a thermocouple reading, so this is normally encountered in electrical engineering, and in the case of the CHE, the injection of a tracer dye. So it's a disturbance that just happened for a fraction of a second. It's not sustained, so its effect could be approximated to that of the impulse forcing function response. So if you're going to collapse, this time element here for the pulse, as it is like more or less like it's going to approach zero because it's very small, what you'll be producing is this line, a line that extends infinitely upwards, a line whose height is infinity and whose area here is equal to 1. This is the representation of the impulse function, Dirac delta function. It's a derivative actually of the step function. So its Laplace transform is 1. So if it has other magnitude other than 1, then the Laplace transform will be the magnitude of that particular impulse input. Its response is like this. So since it's something that extends infinity upwards, the decrease in the response is really notable. So it's an exponential decrease in the value of the response, because your response in this case, class, is y of t. For this particular function, x of t equal to Dirac delta function of t. So the response is e raised to negative t over tau if it's represented by an impulse function. If the step function, since it's mentioning that the impulse forcing function is a derivation of the step forcing function, if the step forcing function exhibits an exponential increase for the response, its derivative will have an exponential decrease in the response. So there's a decrease in the value of x after some time. So that decrease would be, of course, expected to be asymptotic to the value equal to 0 after a very long time. That's for your impulse input. Now, as a summary of everything that we have discussed, and this is taken from our general reference book by Kauhanor, you have here the 4. I did not include anymore the pulse because we already have the impulse here. This is the representation, the forcing function representation. This is the Laplace of the forcing function. This is the transfer function after you have multiplied it with the Laplace transform of the forcing function. And when this is inverted, this is the corresponding response. So since we're looking into standard responses of first order systems only, then this is the generic representation that we will use for the transfer function of a first order system. It's Kp over tau s plus 1. This Kp can have a value of 1 or as long as or more as long as it is a constant. The numeric value that we see in the numerator here is what we call as the steady state gain of our first order system. So all first order systems have denominators tau s plus 1. Okay? So take note that this y of s that you are seeing is already this transfer function multiplied to this Laplace transform of the forcing function on the first column. If this y of s expression is inverted, this is the corresponding expression that you will be getting. As to their responses, so you have here the step response, you have the impulse response, the derivative of the step, you have the sinusoidal response, and you have here the ramp response. The pulse response depends on the duration of the pulse and the magnitude of the pulse. So that is why it's not written here. It really varies. Okay, so you have here the summary. Okay, the summary or the graph of the summary of everything that was discussed in this slide. So should you have any question, you just drop me a line in our Canvas or in our GC and even in my email. Thank you for listening.